Okay, I think we'll get started. So we've been working on putting acids into water and bases into water and getting the pH. Now we're going to finally be able to react acids and bases. We are still going to be restricted to some special cases, but as we build a little further, then we'll be able to get more general cases. But this is a good step for us today. And it's going to be largely just looking at some examples. And then I really encourage you to find the section in your book and work a bunch of problems. We will do one thing that isn't going to be in your book. So I'll try to have some extra problems in the homework set for that attached to these notes. And that is reacting a weak acid and a weak base. But the first thing we're going to do is react a weak acid with a strong base. The reaction of a weak base with a strong acid is very much analogous. So in your homework sets, or in your homework from your book, or the practice problems from your book, you'll be able to see both examples. So this should be enough to get us the basic ideas down. And we're going to first look at a weak monoprotic acid with a strong base. Then we're going to look at a polyprotic acid case. And then finally the weak acid, weak base case. Okay, so let's start with the monoprotic acid, weak, and a strong base. And we're going to look at the case, the special case, where we put precisely the same, we put stoichiometric amounts of acid and base. So if it's a one-to-one reaction between the acid and the base, we put equal amounts of moles to react. So this is special, obviously. Usually we would have an excess reagent and a limiting reagent. We will get to that when we start talking more about this, and in particular about something called the titration. Okay, so let's calculate, say, the final pH. What we're really saying is here, let's just calculate the concentration of hydrogen in this case. And but we could concentrate any concentration because we'll be building it out of an ice chart. So what's the final pH? Where we add 25 mils of 0.1 molar niacin and 25 mils of 0.1 molar sodium hydroxide. So sodium hydroxide is the strong base here. So we know that this will completely break up and we will have 0.1 molar OH minus. Niacin is a weak acid and it has a Ka of 1.4 times 10 to the minus 5. So it will be mostly as niacin, but some of it will break up. And that breakup will react then with the strong base. So let's write the equation first. So here's niacin. And I'm going to call this Ni down below here so we don't have to write that so much. And this will react with the sodium hydroxide. And it's going to be 1-to-1. See, 1 mole to 1 mole monoprotic. And this is a monoprotic base as well. Now, it's helpful to write the net ionic equation. So we've got our Nia. We've got the NaOH minus, so our niacin, which again I'm going to call Nia, OH minus. So the sodium ion here is a spectator ion. I'm going to call this Nia, so this is Nia plus, minus in what follows. And then water stays part of that net ionic equation. And so our net ionic, so then what we do, this should be minus, we're going to take, and here's the strategy of this. We're going to say we have reacted completely with the base, right? So we're going to take our reaction past equilibrium, and then we're going to bring it back to equilibrium. So we're going to take the reaction and say, let's react all the way. So we're going to react every bit of base with acid. Since we have stoichiometric amounts, we're left with only water and the conjugate base to niacin. And that's it. And so then it becomes a problem of, let's go back to equilibrium as if we had introduced just the conjugate weak base problem. So this takes us to exactly what we've been doing before. So whenever we're reacting a strong acid with a weak base or a strong base with a weak acid, as we're doing a strong base with a weak acid as we're doing here, then we take and slam that reaction over and then come back with the conjugate acid or base as appropriate. In this case, we're going to come back with the conjugate base. So here's So it's going to be as if we added pure unprotonated niacin. So that's going to actually come back a little bit with a Kb. So we have to get the Kb, but we know that for conjugate acid-base pairs, Ka times Kb is Kw. So Kw over Ka is Kb. So we can calculate here by using the Ka here, and remember Kw is 1.0 times 10 to the minus 14. That's the auto-dissociation of water. Okay, so now it just becomes a regular problem. The one thing we need to do is figure out what is our concentration of the conjugate base here, of the deprotonated niacin. Well, we've added 25 mils of the 0.1 molar niacin and then 25 mils of the base. That did not contain any niacin. So basically it's a dilution problem. So we could do M1V1 equals M2V2. We'll write it out a little more explicitly here. So we have this many liters of the niacin solution. Here is the molarity. So our liters will cancel. Now I have moles of niacin, because that's what we started with up here. But I want moles of deprotonated niacin, but it's 1-to-1 with this reaction. So our stoichiometric conversion here is 1 mole to 1 mole. And so this gives me 0.0025 moles of the deprotonated niacin. Now, where did that go? It went into the final beaker, which has a total of 50 mils now, because it was 25 mils of the niacin solution, 25 mils of the base. And so that's 50 mils. So that's this many moles per 50 mils. And so we get a 0.05 molarity of our conjugate base. Right? And we would have gotten this with the M1V1 equals M2V2. But here we want to see explicitly where that all comes from. Okay, so then it's a problem like we've been doing a lot. So let's write our ice chart. Nia minus is 0.05, as we just calculated. 0, 0, got a minus x, x. So 0.05 minus x, x and x. And then we'll use our conjugate base, Kb, which is 7.14 times 10 to the minus 10th. And so we can write that out here. We get the physical solution. Turns out it's 5.97 times 10 to the minus 6th. What is x? Well, x is the concentration of niacin. It's also the concentration of the sodium hydroxide. So we can get POH by taking the negative log of that, 5.22, and then pH by taking 14 minus that. And there's our final answer. Slightly basic, as we would expect. So let's gain some intuition about this. We are putting the same amount of acid and base. So if these were strong, they would exactly cancel each other, and we should get a pH of 7. But it's a strong base and a weak acid, so we should be to the basic side of 7. So we should get a pH that's greater than 7, as we did here. The other intuition we can gather is, okay, why is there some niacin around? Well, certainly the base will want to react with it as much as possible, but it doesn't go all the way. Right? There's got to be a little bit of niacin around, and that should be a very small amount, and in fact it is. Concentration of 5.97 times 10 to the minus 6th. And so it's mostly conjugate base. So if we wanted to get what is the concentration of the conjugate base, that basically hasn't changed, because it would be 0.05 minus this. So essentially we have 0.05 molar conjugate base. So we've put a strong base in, we've converted basically all of the niacin over, except a little bit that comes back, but that will influence the overall pH. Okay, well, let's do this problem now for a polyprotic acid and a strong base. And we're going to go stoichiometric on, let's say it's diprotic. So we're going to use vitamin C. So our example here is going to be vitamin C, which can lose 2 hydrogens. It's got 2 Kas, Ka1, dominates over Ka2. as we've talked about before. And we're going to add the stoichiometric amount so that we have twice as many moles of the sodium hydroxide as we do vitamin C, so that we fully react all of the protons, the 2 protons off of the vitamin C. So if we write the overall reaction, we would have the vitamin C, so this is Vit C, and 2 sodium hydroxides, okay, that we're writing the net ionic here. So there's our 2 OH minus. This is we're going to call this Vit C2 minus, right, just for shorthand notation, and then our water over here. So just like back over here, we have to figure out the new molarity of this slammed over reaction all the way to vitamin C2 minus, fully deprotonated vitamin C. So here's our conversion. Here's our original amount, 25 milliliters. Here's our concentration. Here's our stoichiometric ratio. 1 mole of vitamin C will produce 1 mole of vitamin C2 minus when we're all the way over. And so that gives us this many moles of vitamin C2 minus. Well, either M1V1, M1V1 equals M2V2, or what we did over here, and we get to concentration of vitamin C, 2 minus. Okay, well, now we've slammed this all the way over, and again, now we treat it not as an acid-base reaction anymore, but just as a polyprotic base reaction, so a diprotic base in this case. So we will have 2 KBs, KB1 and KB2, and we can calculate those via the conjugate acid, conjugate base has to multiply together to give the water dissociation. And from that, we can get KB1 of 10 to the minus 10 and a KB2 of 10 to the minus 3. So this one is going to dominate. So we've got just this base in water, nothing else around at this point. And so we can treat this by just considering this KB. All right, so this is the reaction that's going on that's governed by the KB2. We're not going to go all the way back. We will, some of it will, but it'll be so small because of the big difference in the KBs. So we do our ice chart again. 0.05 minus x, 0.05 minus x, 0xx, 0xx. And 10 to the minus 3. So now the physical value for x, which is representing the OH minus concentration, is 1.05, 0.015, and we take the log of that, we get 1.28. So 14 minus 1.28 is 12.18. So pretty basic here. And that makes some sense because let's think again here now. We have added enough base to take us all the way over, completely react with both protons of vitamin C. Vitamin C, the second proton, is a very weak acid. So by putting this much base to get all the way over, we are going to be quite basic, more so than we were over here. So quite basic over here, because this is a very weak, the second proton is very weak acid. And so we expect a pretty high pH, and we got it. All right, so again, these two are very common. They're in your textbook, so practice those a lot with those sections. Feel good about it, get good at it, try different ways these problems come at you. So by working a few problems, I think you'll get pretty fast at this. We have to now take a different approach, and this is not actually going to be in your Gen Chem book, but we're capable of doing this. Let's say, what about a weak acid and a weak base? So let's react this niacin with ammonia, and we know ammonia is a weak base. And so let's react 25 mils of 0.1 molar niacin with 25 mils of 0.1 molar NaOH. So again, this is kind of contrived. We're at stoichiometric ratios, but an important case nonetheless. We have the Ka for the niacin and the Kb for the ammonia. Right. So here's our data that we can get from the internet or handbooks or our Gen Chem book. What are the Ka and the Kb for the weak acid and the weak base? Now, we can't do something like we did here because there isn't a strong, fully dissociating acid or base here. We have a multiple equilibrium. So let's write the reaction. Okay, niacin plus ammonia goes to niacin deprotonated plus ammonia protonated, or ammonium ion. But we don't know, so the question is, what are the concentrations? Well, we need to know the K, right? And we don't know the K. But we've learned about Hess's law now. And so we can add reactions to make this reaction. And when we add reactions, the thermodynamic properties add, like delta G and delta H, but the equilibrium constants multiply. So let's reconstruct this reaction over here. So there's our target down here, right, is this. So I want a niacin on this side, and I know the weak acid reaction. And that's given by the Ka, right? I know that. I have the ammonia reaction, and that's given by the Kb. So I do know the K for that. And then finally, what do we have? Well, I've got my niacin, I've got my ammonia. This side, I've got my products, but I also have a water and H and OH minus. So I have more than I need here in my reaction. So I need my third reaction for Hess's law, which is going to give us our, these are going to cancel then. So we end up canceling what we don't need, and we actually indeed get this reaction. So by multiplying these through, we get Ka times Kb over Kw. And note now, this is not, you might say, oh, isn't that 1? Kb times Ka does equal Kw. That's only for conjugate acid-base pairs. So these are not conjugate acid-base pairs. Niacin, ammonia is not the conjugate base to niacin. So this is the Ka for niacin, this is the Kb for ammonia. And so we can get this ratio, and that will be the K for the overall reaction that we're interested in. And then it's just ice charts like before. So we've got the K. So you use Hess's law to get the K, then do our ice chart. I'll skip the step here. We've done this now twice of figuring out what the new concentration is. These were 0.1 molar. This beaker has niacin, this beaker doesn't. This beaker has ammonia, this beaker doesn't. We mix them. It's essentially a dilution for both of those by a factor of 2. And so there's our 0.05 molar starting amounts. And then our final product, we have 0 of the unprotonated, deprotonated niacin and the ammonium. Our change, minus x, x, and x, 0.05, 0.05, xx. And so we get our equilibrium equation as 2.5 times 10 to the 4th x squared over 0.05 minus x squared. When we do that, we get the physical value of x to be this. And so then we could calculate the concentration of all the species that are in the beaker. Niacin would be 0.05 minus this, so 0.004. So essentially 0 in terms of sig figs. Let's play a little loose with the sig figs here to say that there is a little bit of around. Same with the ammonia, a little bit around. And then mostly product. So this, we see that K is very large, very product favored. And so we end up with almost, but not quite, almost full conversion over to ammonium and deprotonated niacin. As we would expect the reaction to shift way over there, because we're reacting an acid and a base, which is a very favorable reaction. Just, it's weak acid, weak base, so it won't be completely over like it is with a strong acid, strong base. All right, so this now is, we've done some actual reactions here, but notice what we've done. We've just essentially made it like the stuff we were doing before by slamming the reaction over, then letting a conjugate base come to equilibrium in water, so conjugate base in water. And then here we incorporated something that we talked about last lecture, which is Hess's law, to build a K that we didn't have. So we build the reaction up out of the Ka and Kb for the weak acid and the weak base. And that gives us an overall K, and from that we can get the final concentrations of our weak acid, weak base, and their conjugate pairs. All right, so that's it. We will continue to talk about this, and just to foreshadow a little bit, what if these don't match? Well, that's very important, and we're going to start talking about, in a bit here, we'll talk about titrations, which is a laboratory technique that will be a great example for having different amounts of strong base with weak acids, so non-stoichiometric amounts. So that's important, and we'll get to that shortly.